to me, this is the bread and butter. Of course, I'm also an engineer, so understanding how water moves with the rain and everything, maybe that's a little bit it, but really this was focused on the hydrologic effects that we cause on the land and maintaining the natural hydrology of a site. So this is the basis of the design stuff. You know, the economics and all that go outside of this, but this is the basis for most of the design and the practices. So this is a little different version of what I showed you before. In a typical forested land cover area, annually you probably get about 38% evapotranspiration off of the with the uptake and the interception from the trees. You have a subsurface flow of about 26%. Groundwater is about 36%. A lot of water goes other places other than surface runoff. There isn't a lot of runoff through a forested land cover area. You start building, and you change all that. So you have urbanized land cover. This isn't completely urbanized, but it has removed a lot of the vegetation, built some impervious area, and now we've changed it to 25% evapotranspiration, only 15% groundwater contribution, 30% interflow, but the big thing is 30% surface runoff in this particular example. You could run the numbers all day long of different land changes, but this is the bottom line. You dramatically increase surface runoff and often take away groundwater contribution. And that's what we're trying to replace. So the principles of LID are to have a groundwater recharge volume. These are what I would consider design principles, but they're the components of the hydrologic response of the site and of the watershed as a whole. Water quality protection, which is taking the pollutants out, doing what you need to do to intercept pollutants or keep the pollutants out in the first place, which would be even better. Channel protection, which I'm going to go through in a little detail because that's a lot of the criteria, is what the criteria is based on for maintaining the site. When you get beyond this level, when you get into flood protection is a little different animal. Obviously it's something we have to do, but it also has to do with how close everybody has built to the waterway, what floodplain are you in, and there will always be floods. There's always a bigger storm. But what we do here, from here up, will limit this to some degree, okay? And we'll talk about that. So, also, you can see there's some criteria here. So, like the annual pre-development recharge rate, you could implement a design criteria for when a development comes in to actually do something for groundwater recharge. But what I have found is that if in the course of doing these two things, water quality protection and channel protection, you just maximize your infiltration, that will get there, for the site. You don't make it too complicated then. You don't add another number that you got to try to balance. Do these, use infiltration as much as you can, we're probably good. So this is what happens in a stream. This is we're starting to get more, you saw a version of this a little bit ago. This is an example that one of our hydrologists did for us a long time ago. The typical, for this example, it was, and I apologize, I forget the land use that it was done on originally. I believe it was either forested or meadow. The response this is a 2-year flow, and the 2-year flow is going to be important. I'm going to be using that over and over again. I'll explain why in a bit. Was the rate of the flow during a 2-year event was 2.3 CFS in the channel. And then it slowly, you saw that long tail come off of this rate. The area underneath this curve is the volume that ran off during that storm. Something else that's going to be very important that we're going to talk about more and more. So the thing we started doing that I talked about was put in those extended detention. And for whatever reason, in this example, they limited, without extended detention, without any control, this is the response you get. A huge, 13.8 CFS versus 2.3 CFS. And if you look, all the area under this red curve is the additional volume that was added. Whatever reason, we only limited, in this example, to 3.9 CFS. Big help as far as that hammering effect, that flashiness, from that perspective. But by putting that there without doing anything about the volume, we still have this increased volume, and we discharge to the river at a higher rate for a longer period. And that's why detention itself is not good enough, because we are still exerting forces for a longer period of time, a different flow regime in the stream over time that causes destabilizing effects, additional erosion. And if you do extended detention enough, so if that was the method of choice, and I'll show you in just a minute why, the peaks would be changing. You would change your time of concentration, which I will explain, and so that you may actually cause a bigger problem as that time shift occurs. So if we can maintain this as closely as possible, the chances of that happening are very slim. This is the effect of what happens as uncontrolled development occurs. A natural system, very generalized. You generally have a floodplain, floodplain, low flow channel. What's called the floodplain limit in this example could be established as a couple things. Maybe the 100-year floodplain, which is what we normally use for building requirements. There's some morphological criteria you could use to describe that. But what happens then is when we build without any of the proper controls, without maintaining the hydrology, we lose the low flow level. We minimize that, or we reduce our low flow rate. We erode the stream, cause a larger stream area, and our floodplain limit goes up. We cause additional floods. Okay? Or flood more often. Okay, I'm going to explain to you as quickly as possible. I'm going to make you all morphologists here in about 3 slides. This is why the 2-year flow is important. This goes to channel protection, so I'm kind of jumping the gun a little bit. Every stream has a predictable pattern, dimension, and profile. What we've learned is we can figure out what that is if it's stable. Stability, as far as the stream goes, is it maintains these dimensions. It might move. This might move downstream, or this pattern may move over time downstream. Might move in the floodplain if it has that, but it'll maintain that pattern. It'll maintain this cross section, and the slope will stay the same as it does so. It neither aggrades, fills up with sediment, or degrades, erodes. That's all. Those features are all described at the bank full elevation. What's the bank full elevation? Just briefly, also, just so you know, little advertisement. A stream needs to stay in balance, also, between the sediment and the water. Everybody knows a stream moves water, right? What you don't think about is it moves sediment. So all streams will erode a little bit. All streams will use the sediment that's contributed to it from the land and move that. It has to have it. Downstream of a dam, if you look downstream of a dam, the stream often has a plunge pool and it's often wide. Why? Because the dam takes away all the sediment. It's called hungry water, and it'll cause erosion there for a short distance until it can start picking up sediment again. So I'm showing this slide just to remind you that all erosion is not bad. But there's always some, and remember that stream is moving. It's that dynamic equilibrium. So it may erode here, but it puts it back down here. You know, so there's that action going on. Okay, keep that all in mind. This I could go through in great detail, but what it really gets to is that it takes that sediment transport rate and the amount of times the flow event occurs and determines that the effective discharge is between the 1 and 2 year storm event, flow event, I should say. The 1 and 2 year flow of the river. This is where the 2 year flow comes from. So for channel protection, we've based the 2 year flow, which is probably the maximum. There's should be no stream in Michigan, a natural stream, that would have a recurrence interval to maintain that stability of greater than 2 year storm, 2 year flow. That's where that came from, for those reasons. So that was a quick morphology lesson. This is just defining what the bankful stage is in a very brief way. Sometimes it's not as easy to see, but it's the part that just fills the channel and starts to go on a floodplain. In some streams that are beginning to become disturbed, it might be very tiny, but it's still there. It's apparent on almost all streams except mountain streams, and we don't have too many of those right here. So the bankful discharge is the momentary maximum flow associated with that elevation, and it recurs every 1 or 2 years, and it's the part that does the most work. So it's considered the effective or channel forming flow. So if you change that with the hydrology, by changing the hydrology, so now you've made this flow the 6-month flow or the 3-month flow, the stream will try to adapt to what is now the new 1 or 2 year flow. And if you maintain that super high peak, that flashy peak that I showed you in that hydrology thing, the hydrology chart, that hydrology thing.
We got it.
It might not be able to adapt. If anything, that's a mountain stream. A mountain stream may react that way to some extent because it's all hard surface and everything. But the mountain would turn into a step pool system and has hardened structures. You try to do that in the sand you have around here, and it'll never stabilize. So, okay, and that's basically what I was using that again. So, yet another view of the site. We want to, in this case it's the size of the arrows, we want to make this arrow and even these as close as these as possible. But we're going to use surface runoff for most of our design criteria. To maintain pre-development hydrology, you need to do 3 things. You need to maintain the time of concentration. This is kind of an engineering thing. We said there's going to be no math. We are not actually going to do the calculation, but we are going to kind of talk about the formula. The time it takes water to get from the farthest point in the watershed to the point of collection. So, in a forest, a drop of water, first of all, you have to get enough rain to have runoff at all, because some of it will soak into the ground. Then when it starts to run off, it goes through all this vegetation that slows it up. And hills and valleys, micro hills and valleys. Slows it up. You clear that, take away all those micro hills and valleys. That makes it happen faster. Now you pave it, makes it happen quicker and faster. and changes this number. So, important number, remember. Volume. This is really important. I'm gonna emphasize this over and over. When we take away the vegetation in particular and the ability of the water to go into the ground, we have increased the volume of runoff, the amount of water that's coming off of the site. And it's going to be huge. That's going to be the biggest thing to focus on to control. And then rate, which is the highest flow. Still important. We still have to control that because of those peaks you saw, the flashiness. So how do you control time of concentration? By maintaining natural drainage paths. Like we showed some examples of this in those example designs in the first presentation. Using open swales. Those things, open swales, full of vegetation, has a little bit of microtopography, even slows up the water, and it allows some water to infiltrate. Increase the surface roughness. Various ways to do that. Even if in some cases you're doing it with rock, in certain drainage paths. Detained flows. Detaining flows does have a place, even though I talked about the negatives of detention. On-site has a place in some designs. Minimize the disturbance. So if you can leave the big trees, that is really going to help you a lot. Flatten grades in disturbed areas, so you don't have a steep slope. Disconnect any imperviousness, and connect pervious and vegetative areas. So your runoff from or your lost my thought. Sorry. The example here is, instead of a curb and gutter, this is a very, very simple system. The water runs off this road in sheet flow, so it's going through the grass. Even though this is lawn, it would have been better if we had a little bit more rigorous vegetation, some nice plants, deeper rooted vegetation, but lawn still works. It slows it up, allows some to infiltrate, and if you saw this up close, you'd see that that's not quite at ground level, it's a little higher, so it makes it come up at least a couple of inches before it starts flowing through that. That reduces the time of concentration, and in this case, volume as well. Put a curb and gutter on that, put it in a pipe that goes out, lickety split. To figure out rate and volume, most often you need some form of a hydrologic model. Once again, no math. We're not going to get into any math. The one most often used is the NRCS curve number method, which predicts volume. Curve number predicts volume. It's often used in TR55, it's used with the unit hydrograph to predict rate and volume. In fact, these four models, they increase in how rigorous they go. The HEC HMS or SWIM are very complicated, rigorous models that are used for system-wide, generally, calculation. They still use the curve number, or can. You have some options to use other methods. But the curve number is dependent on, and I'll go through the curve, what a curve number is in a minute here. But one thing about the curve number is that it doesn't work well at flows below an inch. It over-predicts. It might not be a problem if you're trying to figure out relative differences, but if you want, a guy named Robert Pitt came up, if you wanted to be more accurate and are only dealing with those lower flows, there's a small storm hydrology method is another method for calculating it. I will say that this is where I have to give my inner college professor's speech. All models are wrong. Some models are useful. So these are models. Curve number, in my mind, gives you a very good estimate, even at those lower levels, for design purposes. To get the amount of water out that you need. But if you really want to know what the water is, you're going to have to go to something, either a more rigorous model where you can turn a lot more knobs and whistles, or something that is designed for that purpose. Okay? That sound good? The rational method is widely used. You still using the rational method? Yeah. It's very good for pipe design, but it was designed to predict peak. It's been modified in a couple of ways to provide volume. It is not as good a method as NRCS method, as curve number method to predict volume.
Ralph, I always thought rational method 2 was generally limited to extremely small areas.
Yes.
Yeah.
Well, not necessarily extremely small.
Most people are supposed to, and it's like parking lot.
It's not. You can't go too far out. Right. So, for purposes of low impact development, I generally avoid it. There's ways to use it, and it will probably turn out. It could turn out okay. Curve number method is what I normally depend on. In Michigan, we've taken the TR55 method essentially and modified it slightly. If you'd like to use that, it's more geared towards, it's tweaked a little bit for Michigan geology and rainfall. Probably needs to be tweaked again, because although this was the chart that I normally use to determine rainfall in Michigan. You can look this up a couple different ways. We have it on it's out of Midwest Bulletin 71 from 1992 though. But you can still use this. This isn't that far off, but it's changing because of climate change. If you look at NOAA, it has recently updated their atlas to change the precipitation. They're all going up. They haven't gone up a whole lot at the 2-year level yet, but they're all going up. And NOAA no longer provides it at least at this level of distinction. They do it in a much narrower level of distinction. So you can go to their website and click anywhere on the state, and they will give you a much more precise measure of what the rainfall and recurrence interval is in order for that.
I think it's almost down to section level.
It's down a lot.
It's real small. Our floodplain engineer uses it all the time. I was amazed at how much more detail it is in terms of specific locations. And
it's based on all those numbers are a weather station, and the new numbers are based on lots more weather stations and how they interact. So it's better to go to that site. These numbers still aren't bad for our design purposes as long as you're staying down here. Flood flows are a little different. They're a little higher. But.
So obviously it's probably more for the engineers in the audience, the few of them that there are. But I want to point, Ralph's mentioning this, and for the non-engineers, the people that were talking about code a little while ago, I think this is unbelievably important. The statistics show that because of climate variability, these numbers are about 25% too low. So most codes are written to these numbers right here. These numbers right here are based on data records before 1992. Okay? If you just follow this train of thought for a second.
Long before 92.
So you're looking at, we had like 30 years of records, the 60s through 90s. Okay? Engineers, for you guys, or for any infrastructure projects at all, are using data that's 20 or 30 years old to design systems that are supposed to last for 30 to 50 years. So we're using data that's 30 years old, that's wrong, to design things that are supposed to now last for the next 30 to 50 years. And that's what the codes are telling us to do. And it's incredibly flawed. So just kind of keep that little nugget in the back of your head when you're talking about site plan review or development, that what is currently told, what the county drain commissioners are doing, what the DOT is doing, is really inaccurate and inadequate. So just kind of keep that nugget in the back of your head.
So I'll take it a step further. Not only are you using old data to predict what you're going to use for 50 years, but probably they're changing. If the climate change predictions are true, over those 50 years it's going to continue to change and probably go up. This has been the typical design criteria we use? A 24-hour storm?
24-hour storm.
And remember, this is all statistics. It's regrettable that we use a 2-year recurrence, because a 2-year recurrence could happen 4 times in 1 year and then not happen again. You know, it's a statistical measure of how often it would happen. If you're looking at a 2-year event, for instance, it would be a 50% chance that it would happen in any given year. That's
But for
really what
most
it comes
things,
down to.
we use that, those would all go with the 24-hour storm.
Correct.
Right. But there's also I'll give you an example, instead of a 50-year 24-hour storm, which you guys up there's a 50-year 1-hour storm. There's a 50-year 12-hour storm. You know, there's this whole family of storms depending on how long the duration is.
And those storms are becoming much more intense. That's the change, but we're not designing to those right now, and that may be something we have to take into account for the future. Because if that's where we're headed, if we're gonna get, instead of soaking rains, planning for that, we're getting very intense, short duration storms, we may have to plan our infrastructure for that, to respond.
Well, and this whole thing too, you know, as we talk about climate change, rising temperatures, things of that sort, then you have, how do you fit in the equation of evapotranspiration then, into the whole thing? Because that should be increasing in theory.
It goes up, right?
Correct.
Yeah. So that's part of the modeling, but that also looks at a longer duration, right? So we're talking, you know, when you have that intense storm, that's what's hitting your surface in that moment in time. And if you have nothing but gray infrastructure, that's what's crushing your streams right away. The ET is going to go up, but that's going to go up over the next couple of days and dragging it out. One of the other ways I like to sell this, and again, I know I don't want to get into the weeds of engineering, but here's how I sell this to a lot of communities, is a lot of our infrastructure, gray infrastructure, is designed for the 10-year storm. That is what it's designed for. So a lot of people will say, well, it failed. Our infrastructure failed. And my response is, no, it didn't. It wasn't designed for that. You got to remember, everything is designed for something. And so a lot of our infrastructure is that 10-year infrastructure. So what I like to do when I preach for green infrastructure design is looking at the green and gray in combination. If we can put in green infrastructure LID to account for 2 inches of rain, okay? And you got this chart up. I can actually do this in a level that, you know, public elected officials can understand. Ralph is one. We're having this conversation. Right? If I take 2 inches off of everything on this chart, that 100-year storm, if I take 2 inches off of that, it's now effectively 2.36 inches. At 2.36 inches, it's below what my gray infrastructure was designed for. So it's basically putting a layer of green over the gray so that we won't have all of the issues with the flooding. That's kind of the added benefit. It's not ripping out all of our existing gray infrastructure that's failing, because it's not, it just wasn't designed for that. It's shifting that big storm into something that our current systems can handle. And that's something a lot of municipal officials can start wrapping their arms around. Oh, I see now why we need to do this, to keep our roads from flooding, to keep our basements from flooding. And we got one of the biggest, I don't say the best things, it's not a good thing, but we got whacked with 6 inches of rain in southeast Michigan last August. My phone was ringing off the hook. You know, what are you going to do about this? What are you going to do about this? What are you going to do about this? And I'm like, well, first of all, because they all think green infrastructure will instantly solve that. I'm like, no. You know, 6 inches of rain is 6 inches of rain. That's not anywhere.
It's an anomaly. It's out here. It happens every now and then. The Mississippi floods of, well, when was that? Late
1993?
90s? Yeah, the early 90s. Same thing. It was a 500-year event. Those happen. Those are incredibly destructive and change things.
Well, yeah. So the end all point is that this chart can be helpful just to start talking to people about moving the envelope a little bit and what this means for design and means for infrastructure. So.
And I don't think either one of us concluded much about climate change in our talks, but one other point, since we brought it up, is vegetation. Over time, if the temperature is going up, we are probably going to need, and even precipitation, we're probably going to need to evaluate the vegetation we're using for a lot of these things we're planting. And that's going to change too. So we're really going to need help from vegetative specialists. I can't say enough how much we need vegetative specialists. Okay. Yes?
Are the stats, is there a movement to update those?
They are updated. That was really where I was going. If you go to the NOAA site, But they're updated for current, and back, like, they analyze the last 30 years still, or probably the last 20 years, more closely for what they've done. And they're done differently. They're not done on just these 10 weather stations that they were done before. They're done on multiple, like hundreds, literally hundreds. And you can click on the site and get these numbers, it's these same numbers, but for that specific location.
But I think your point is, yes, the stats have been updated, but the ordinance have not.
I was gonna echo that.
The ordinance is not.
That's the problem we run into is when you're trying to regulate this, but the regulation says I have to use this.
Right.
Or I'm only obligated to use this because the regulations have not been updated for the current hydrology.
And the design stuff on that the early part of this talk, the design stuff may have to switch. We may have to account for those shorter, more intense storms, and not the 24-hour storm in some design criteria.
Do you think that it would be worth your while to coordinate with the Planning and Zoning Center at MSU, Mark Wyckoff and those folks, and explain this to them so that they could get the word out to the planners and zoners in the state that ordinances ought to be looked at for this particular point?
So I'm actually working with Mark Wyckoff on a project right now.
Oh, good.
So, yeah.
Good.
So it is, yeah, the hard part is the slowness at which ordinances are developed and changed.
But he might wanna
It's a very slow
consider-
process, unfortunately.
But he might want to consider, he does these, series of classes that they offer, workshops throughout the state. And
I'll see him in June, and I'll actually ask him more specifically about this.
yeah, because it would be good if it came from the Planning and Zoning Center, and they came to the local government entities and told them, it's time to really start looking at this now and, updating these numbers and updating your ordinances accordingly, because you don't want to have your ordinance stop, better development. I mean, you don't want to have those barriers out there, and that's a real challenge. Thank you.
Very good. Any other questions? We said there was going to be no math, and I think we really didn't make you do math, but we did throw a lot of numbers. So any other questions on that? Okay. So, curve number. This is, I hope Don doesn't yell at me too much, but I use curve number, I think of curve number, this is really not an exact way this was developed, but I think of curve number as representing the surface runoff. A small curve number is a small amount of surface runoff. Large curve number will represent a large amount of runoff. It affects these other things too, you could look at it that way, but this is, I said early on in the talk, I'm looking mostly when I'm doing design at the surface runoff. That's what I'm trying to control, because you see how large it gets. And that's what's blowing streams apart and transporting things. So I look at, that's how I visualize curve number. And if you think about it, if we take a farm on a sandy soil with woods or woods even on loamy soil, the conditions would have been the same, with a 2.37 inch rainfall, which was the 2-year storm for this area, on, I believe it was 1 acre, did I say? Maybe I didn't. But on the site, that would have been a curve number of 70. Okay? The time of concentration for that natural condition is 0.75 hours, 3/4 of an hour. The flow for that condition, 23 CFS, the volume is 5 acre feet. Okay, so now we develop. And we change the curve number based on the development. We add a lot of imperviousness. Now the curve number's gone up to 86. We were able to do that without changing our time of concentration. But the flow went up to 65 CFS, so the rate at which it ran off went up almost 3 times. And the volume more than doubled, 11 acre feet. And that's represented here. The volume here is this whole area underneath this curve, where it used to be just the green part. Okay? Now let's take it a step further. Let's do the same development, but we weren't able to maintain our time of concentration. It increased by 15 minutes. So now it's a half an hour. the volume goes up. I'm sorry, the rate goes up, the volume does not go up. The rate went up to 90, yet again, a third more. So, and the peak changes. And this is where, if we used extended detention, we start to get issues. If we only bring the peak down but don't change, but that the time of concentration is changed, and you do extended detention, without respect to each one of those things, you could change the peak ultimately so that they all line up downstream somewhere at the same time and actually increase the peak down there. So, we need to put practices in that maintain the curve number at 70 and the time of concentration at 0.75 as close as possible. So we change that minimally or not at all. Okay? So that's how the model works. That's how curve number works. What the curve numbers look like, there are a number of places you can get this information. In the TR55 manual has a whole lot of these. It's listed on the NRCS website. So if you have a manual meadow, and these are soil groups that I'll explain in a moment, but basically A soils are highly drained, and D soils are very tight, clay soils. So A is like sand, you got a lot of A soils around here. Very, very easily drained, sandy soils.
But does that also include water table, like, isn't it, like you get into a muck or something like that, or a wetland soil, that's gonna be in the hydrological group also, isn't it?
Correct.
Yeah.
Or it gets even a little more complicated, you have a D/B, because it's really D soils, but they're drained. You know, you've got,
Right.
so you
Right.
have some of those issues, but basically for our purposes, the curve numbers are based on soil type, and then what's on the land. So what the curve number really tries to do, for better or for worse, is pack in everything that could be happening to affect runoff, so that it is accounting for some infiltration, some vegetation, or building. You know, if you have commercial business, you see how the curve numbers go up quickly when you get into development. And water's the only thing. Something about a curve number. So you have paved areas. Paved areas are 98. This is not percent runoff. This is a curve number. A lot of people look at it like that though, but you never have. If you do get 100, it is 100%. It's not quite percentage on these lower numbers. 90. You never have total runoff from anything except water. If you have water surface, obviously everything that hits the water stays on the water, so that's 100%. If anything else, you have little cracks, or the concrete has pores in it to soak up at least a little bit. But you were going to say something.
Well, I was gonna say that not only paved, but even a compacted gravel road, that curve number is very, very close.
Very high.
98. Yeah.
Yep, very high. Yep. Okay, so that's how the curve number works, and there's a lot of criteria. I'll tell you one other thing in the models. There's two ways to do curve numbers, and even some of these are done this way. In this example, there's a composite or a weighted. And if you're comparing two, kind of like a ag field and a residential yard, a composite might be okay. Basically what a composite is you take the area of each one and multiply it, multiply the total, multiply each portion of that, and make a new curve number for the total land area. Okay? That's okay if your land uses are close. Almost any time you're comparing pavement to anything else, you should not do that. Because the change is so dramatic, you should calculate, it's called weighted, and you calculate the runoff from the paved area and calculate the runoff from the vegetated area and add the two together to get your total. Okay? But that is getting close to math, so I'll move on. in order to determine the volume, the curve number portion are these formulas, but this particular spreadsheet is an adaptation of the spreadsheet that was in that lid manual, the SEMCOG lid manual. It's live on the DEQ website, and you can plug in for soil type and curve number. You can plug in area, the area you're looking at. You can calculate the difference in the pre and post development and get your volume that you need to control. Now this is the method, but it's also, if this is all you do, if you don't calculate the rate and you do the volume, the rate won't be controlled. I think I showed you on those other graphs that if you control the rate, the volume will not necessarily be controlled. That's why volume to me is the most important. And not only that, but the impact that volume has on the river system. But if you control volume and you control it at the site level, you're probably also controlling time of concentration. Okay? Because you're taking that volume out, you're actually taking that water, that excess water that you've generated out of the picture. You've put it somewhere else. Okay? So, volume. And this will calculate volume. This spreadsheet does not calculate rate. It only does the volume portion. Okay? The small storm hydrology method, I won't go, it really gets close to doing math, so I'm not going to go over it very much. It's available a couple places in the SEMCOG manual if you wanted to do something a little more exact, a little different calculation. All I was really going to say here, high curve number, low time of concentration on the two development methods. How do you reduce volume? Infiltrate, we've already talked about that. Evapotranspirate is really what this should say. So you're intercepting with vegetation, evapotranspiration. Reuse, didn't talk about that a whole lot. Are you going to talk about it a little bit? And so you'll hear more about that. Little more complicated how you figure it out, but all a very important tool in the toolbox also. This is just an explanation, like I promised, on what the different soil group classifications that NRCS uses and some of their infiltration rates. I'm going through this very fast because I know I'm running out of time. I wanted to caution you though, in some designs, depending on how rigorous you need, there's different ways to actually measure infiltration rate. Those soil groups sometimes could really be off. It's good for planning and figuring, but what's actually underneath, a lot of those are at the surface and very far down. You might have a water table, you might have bedrock. You really should do an infiltration test of some sort. I won't go into that very much right now. You can do something rigorous. You can also do a bucket and a post hole digger, bucket and a stopwatch, and figure out your infiltration rates to make sure that what you're designing. I want to go through these two very quickly because I also want to point out the value of vegetation. If you had a meadow with a curve number of 71, and I think this was a 1 acre site for the 2-year storm, and we know that that's the most important storm for volume, right now. If you completely pave the site, you change the curve number to 98, you would increase the volume that you would add would be to this would be 5,500 cubic feet. You should be able to accommodate that with roughly 20% rain gardens on 20% of the site, depending on different design criteria and what you have available to you. Okay, so you would give up only 20% of that, which is also probably close to what traffic islands right now would take up, and other attributes that you would work in to have no or limited lid control. But the other thing I wanted to point out is that if you had open space and that you basically an abandoned lot that had a curve number of 79, and you just went and planted a bunch of trees on that site, you would remove over 1,000 cubic feet of volume. by the interception from those trees and the uptake of those trees. And that's just with the curve number calculation, okay? For the two-year storm. Very important. Vegetation. Can't say enough about it. The dancing elephants for a brief moment, but I've already gone past my time, so I'm going to very quickly let you know that I want to get into quality for just a moment. The runoff quality for most of these practices is designed in a different way. We don't ask you to measure it. That's measured. Don does a lot of studies and things like that to let you know how effective they are. We know that most of the storms, 75% of the storms are 1 inch or less. So if you capture this, you would treat 75% of the storms or less. You would take out 75% of the pollutants. Not only that, but most of the pollutants are, you've heard of the term first flush. I'm sure almost everybody in this room has heard that term. If you take a dinner plate and put it under the faucet, at some point it's clean. You're rinsing it. Same thing happens on a parking lot. Can't say the same on green space, a little different mechanism. But on a parking lot, at some point, the rain washes that thing clean. And the water that runs off of that is mostly just water at that point, all right? There's a number of criteria. You've heard of the half-inch criteria. And a lot of people, that was done early in the late 80s or early 80s to late 90s. Some people looked around and said, nah, that's not really good. You really should use 1 inch. And do you use it over the impervious area or over the entire area? Out east, they came up with the 90% capture, which is essentially determine the storm that produces 90% of the runoff. And these numbers were done, unfortunately, based on the current statistics. They would probably be updated. But you can see that almost that everywhere, it's just less than 1 inch for those 10 stations I showed you earlier. If you captured and treated this storm, you would get 90% of the pollutants, 90% of the storms. You would treat 90% of the storms and more than 90% of the pollutants. Okay? Makes sense to everyone? I'm going to fly a little bit. That's a small storm. That's just a different way of calculating water quality using the small storm hydrology method. It's very quick and easy. I promise no math. Channel protection criteria. When the channel protection criteria are met by maintaining the pre-settlement runoff volume, I didn't really tell you the difference between pre-settlement and pre-development, but we'll talk about that over the course of the day. The water quality volume will automatically be attained. So, if you take out that volume, and are treating it, by the way you take it out, whatever that is, you have automatically met your water quality number. Once again, deal with the volume, and another parameter is taken care of, and you reduce flooding. And these are the mechanisms. I'm going to fly a little bit. Special conditions, tight soils, so infiltration is difficult. You may have to look at more reuse. You can use. There's always some infiltration you can get out of the site, but you may have to look at interception and reuse. Transportation issues because of right-of-ways and cutting across multiple watersheds. There's some issues with transportation and how they actually change drainage paths. Brownfields, always one of the most difficult to deal with because there's contamination issues, but there are many, many ways to implement lid practices and get reductions on brownfields. However, brownfields is the one exception where you may have to at least rely on some extended detention off the site because you just can't get water out other ways because of contamination. And then redevelopment, how you handle redevelopment. And I'm going to skip this example because I've gone through my time, and we're back to the rainy elephants. So, questions before we take a short break?